Today we start from gradient, one important topics of calculus. In previous day we also discussed partial derivative, directional derivative, and also Jacobian. Today we start from gradient. Let C be a non-empty subset in Rn with interior of C not equal to phi, and if C to Rn be a function such that all partial derivatives of f exist at a point C, then the vector del f C by del x1 del f C by del xn is called the gradient of f at point C. Okay, we also now discuss about this gradient in we write in note here. Okay, then grad f equal to grad of fc equal to del fc by del x1 del fc by del x2 del fc by del xn. Okay, let u belongs to Rn and f dash c u equal to u1 del fc by del x1 u2 del fc by del x2 un del fc by del xn. Okay, so this one equal to u gradient of del fc. Okay, u grad of del fc, f dash u equal to inner product of u grad of fc. Then what happened next? Next we erase this portion and going to some properties of this. Properties of differential operator. We write this one now and we also talk about this one. So properties of differential operator. Okay, properties of differential operator. Okay, then let if u subset of Rn, let if u subset of Rn to Rn be a function such that f is differentiable on u. F is differentiable on u. Then the derivative f dash of f, then the derivative f dash of f is a mapping from u to is a mapping from u to u into L of Rn Rm. Okay, here we write Rm then better. Okay, if u to u subset of Rn to Rm be a function, then f is differentiable on u, then the derivative f dash of f is a mapping from u into L Rn Rm. Okay, then we write another proposition. Okay, this proposition is we write here in proposition. So let C be a non-empty subset, that means phi not equal to C subset of Rn, and let and if C to Rm, if C to Rm be a function defined by defined by fx equal to b or b not equal to 0 for all x belongs to C. Okay, then and for some b and b belongs to Rn. Okay, for r b belongs to fx equal to b, then b belongs to Rm. Okay, then f is non-linear operator, and first one this, and second one, f is differentiable at C. F is differentiable at C. Okay, then how we prove this? First we write f of x plus y equal to b for all x y belongs to C. Then fx equal to b and fy equal to b. So f of x plus y not equal to fx plus fy. So f be non-linear operator since f be non-additive. Okay. Now second we also talk about f is differentiable at point C. Since limit h tending to 0, f of c plus h difference f of c y h equal to limit h tending to 0 b difference b by g h, then this one equal to 0. Okay, so now we also erase that portion and going to further discussion of another proposition. Also erase this portion. Now write here proposition. Okay, write here proposition. So now let fg here C subset of Rn to Rm. C subset of Rn to Rm be two functions such that f and g are differentiable at C. F and g are differentiable at C. For belongs to interior of C, and for beta belongs to R. For alpha beta belongs to R, define fx equal to alpha fx and beta gx. Define, okay, x belongs to C. Then f is differentiable at point, differentiable at point C. differentiable at point C with f dash c equal to alpha f dash c and beta g dash c. Okay, then how we do this? Let a equal to alpha f dash c plus beta g dash c. Okay, then we have limit h tending to 0. We have limit h tending to 0 f of norm of f of c plus h difference f of c difference ah divided by norm of h equal to 0. Okay, we have to show that this one. Okay, then this one equal to what we have find equal to limit h tending to 0. This one equal to alpha here alpha f of c plus h plus beta g of c plus h difference alpha f of c difference beta g of c difference alpha f dash c h difference beta g dash c h divided by this one norm of h. Okay, then this one equal to limit h tending to 0 norm of alpha f of c plus h here difference f of c. Okay, difference h f dash c. Then beta g of c plus h difference g of c difference h of g dash c. Norm of this by norm of h. Okay, then this less than equal to limit h tending to 0. Okay, norm of alpha norm of f of c plus h difference f of c difference h f dash c divided by norm of h plus this one beta norm of g c plus h difference g of c difference h g dash c divided by norm of h. Okay, then we erase our portion and going to discussion about that. This one, that portion we also vanish now. Now we're going to this less than equal to norm of alpha epsilon by 2 norm of beta epsilon by 2. Okay, for epsilon greater than 0. Since f and g are differentiable, since f and g are differentiable, so differentiable at c, so limit norm h tending to 0 f of c plus h difference f c difference a h divided by norm h less than epsilon by 2 and limit h tending to norm h tending to 0 norm of g of c plus h difference g of c difference bh by norm h less than epsilon by 2. Okay, oh sorry, here not b, here f dash c, here g dash c. Then this one happened. So therefore f be differentiable, at c, and f dash c equal to alpha f dash c beta g dash c. Okay, again we write d of alpha f plus beta g equal to alpha d of f beta d of g. Then we also see about that one important theorem also discuss now. Now we also discuss if fx equal to inner product of two functions, then their derivative exists or not. We also discuss now by in proposition. So we start this one now. We erase this portion and we also done this one. Then we're going to another discussion about that. Okay, so familiar or important proposition, that means inner product of two functions is differentiable, and how this one is differentiable we also discuss now. Let f and c such that c subset of Rn to Rn, okay, be functions such that f and c are differentiable, at point c belongs to interior of c subset of Rn, and define capital FC to R denoted by fx equal to inner product of fx gx. Okay, for x belongs to c, then f is differentiable, with f dash cu equal to inner product of fcg dash cu plus inner product of f dash cu gc. Okay, for all u belongs to Rn. Then we're going to prove of this. Okay, then we're going to prove of this. How we handle this proof? For h belongs to Rn, with h not equal to 0, then we write here f of c plus h difference ah equal to how much here, f of c plus h g of c plus h inner product f of c g of c in difference a equal to how much, a equal to we write here this one equal to a. Okay, then we write here if c g dash c h, okay, a is equal to, and difference f dash c h g c. Okay, then what happened here, f of c plus h difference f of C difference f dash c h. Okay, and then here we write g of c plus h. Then which term we subtract this one, then we add this one, f of c, here g of c plus h, and plus f dash c h, here g of c plus h. Okay, then difference f of c, g of c, here difference f of c, g dash c h, here difference f dash c h g c. Okay, then this equal to how much? This equal to, we write f of c plus h difference f of c difference f dash c h, here g of c plus h, plus here we write f of c equal to g of c plus h difference g of c difference g dash c h. Okay, and then what happened? What is remaining? Remaining is here plus 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 here f dash c h g of c plus h difference g of c. Okay, then what we get? We erase the above portion, and we also get what? We write now what we get. Okay, then f of c plus h difference f of c difference ah equal to, we get f of c plus h difference f of c difference f dash c h, here g of c plus h, plus here fc, here g of c plus h difference g of c difference g dash c h, here plus f dash c h, here g of c plus h difference g of c. Okay, then what happened? Then norm of f of c plus h difference f of c difference ah divided by norm of h equal to, less than equal to, norm of f of c plus h difference f of c difference f dash c h divided by norm of h, here g of c plus h, plus here norm of fc multiplied by norm of g of c plus h, g of c difference c dash c h divided by norm of h. Okay, plus here f dash c h divided by norm of h, here sorry f dash ch multiplied by norm of g of c plus h difference g of c by norm of h. Okay, we mark that one, this one. Then what happened? Then if, since f is differentiable, so So limit h tending to 0, norm of f of c plus h difference f of c difference f dash c h divided by norm of h equal to 0. And again g dash c, again again g is differentiable, g is differentiable, then limit h tending to 0, norm of g of c plus h difference c of c difference c dash c h divided by norm of h equal to 0. Limit h tending to 0, g of c plus h equal to g of c. Okay, then we erase our portion and we get here from 1 we get limit h tending norm h tending to 0, f of c plus h difference f of c difference ah norm of this divided by norm of h equal to 0. Okay, as that means as h tending to 0, this one is 0. So since y since norm of f dash c h, okay, norm of g of c plus h difference g of c divided by norm of h, okay, less than equal to norm of f dash c h, norm of h, norm of g of c plus h difference g of c divided by norm of h. Okay, then this equal to norm of f dash c, norm of g of c plus h difference of g of c. This tends to 0 as h tends to 0. So what we get from here that f dash c h equal to inner product of f c g dash c h plus f dash c h g of c. Okay, we get here. So this implies that f dash cu equal to inner product of f of c g dash cu plus f dash cu g of c. This one is the derivative of inner product of fx and gx. Okay, so today we discuss first we discuss definition of gradient, then properties of differential operator, then some proposition about nonlinear operator and differentiable at x, then obviously we talk about if fg differentiable then their linear combinations also differentiable, and then also we talk about if fg is differentiable then their inner product also differentiable, and we getting this result after differentiable. We also check all these result clearly and all are understand, I think. So today we stop here and we also discuss chain rule in 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 ongoing classes or in upcoming classes. Okay, we also discuss chain rule. Today we stop here.